So guys, as stated before, the GCC compiler does support general based options as well as specific ones. When it comes to the general options, optimization level are widely used there. Optimization level is the fact of optimizing the final generated ELF or binary file in terms of code size as well as performance. Code size, we are meaning here the size of the final binary to be loaded in the target device, and the performance means basically overall execution time of your program. Now GCC as a compiler does support multiple optimization levels, starting from O0 to O1, O2, or 3, and then we have more extreme and aggressive, let's say, optimization levels like OS, OZ, OFAST, and so on. As you can see in our program, we didn't specify which optimization level to be used. The default for GCC is O0. So almost we don't have kind of aggressive or let's say irrelevant optimization has been done into our final binary. If we are going to do kind of benchmarking and check the impact of this optimization level into our final ELF or binary file, then first of all we need to add the optimization level to be used here. In our case, we will start with O0. So this one actually doesn't do any kind of relevant optimizations into our final binary, and we want actually to see the final disassembly file, how it looks like, as well as the size of the binary itself. This is one thing. Then to see the disassembly, then we need to invoke the object dump to generate the disassembly file out of the ELF file. So here we'll add the tool object dump, and of course we'll invoke it from our ARM-GCC package. So far so good. We go back to the makefile. Here we didn't invoke yet the object dump, so the best place actually to invoke it will be here after the generation of the program.elf. So we'll do the following. We'll invoke basically this guy. Now we need to specify the option -t. It means we are going to generate the full disassembly of the ELF. Then we can specify as input this program. So this is the input. This is how we do it in makefile. And finally, this is the outcome. You can have the same name as the input, but with extra extension d.disas. Now, so far so good. After we compile our project, we should see the .elf file as well as the disas. So let's do it. Okay, let's start from scratch. So this is our project. Make all. Okay, so far so good. Now let's go to the build folder. We have the .elf and we have the .disassembly file. And as you can see, the disassembly specify all the instructions that are going to be used and executed by our processor. Now, one thing to be done is we'll need to back up basically both files. This is one thing. This is going to be used actually for benchmarking. And we'll copy them. Here, and then out of the ELF we'll try to generate the .bin file. For that, we can invoke the Windows command line, or we can actually integrate this as part of our makefile. But for the sake of this experiment, it's enough actually to do the invocation, let's say once or twice, only for the benchmarking part. So again, we need the path to our package, our toolchain package. Then copy. It's called ARM UOB ops copy. Okay. Now to generate the binary, we need to specify the format of the output. It will be -o binary. Then we'll specify our input file, and finally our input file, and then finally our output file. It will have the extension .bin instead of .elf. This is done. So let's see. So this is our bin file. Now to explore or to see this .bin, we need kind of hex dump basically tool. PowerShell, I mean Windows PowerShell has this already integrated, so we can use PowerShell here to dump basically our .bin file. So we need first to navigate to our directory where we have our .bin file. And then we'll invoke the tool called hexdump, then specify the .bin file as input, and then we'll redirect the output to another file we can call program.bin.txt. Okay, let's fix this .txt. Okay, let's remove this. Now let's try to see this one. As you can see, this is kind of pure binary. Of course, we have some hex value here, but they're gonna be decoded later on to some pure binary 0 and 1s. And here, basically, we see the offset. And this is actually the final address or the final offset where we have a valid binary to be loaded. So this tell us about give us actually an idea and tell us about the size of the full binary to be loaded into the target device. Now this is concerning O0. So let's take this out, put it here. Now let's do clean. Okay, done. Now let's go back to our makefiles. No, I don't need it. Okay, now for the toolchain, we will specify another optimization level. So as I have stated, we have multiple optimization levels supported by the GCC compilers, O0, O1, and so on. Now, when it comes to the difference between those optimization level, frankly speaking, so between O0 and O1, I mean, we will not see basically that much optimization. Of course, the compiler will try to do some kind of code size and performance optimization, but it will try actually to keep the same performance in terms of execution time of your makefile procedure. So it means it is not going to favorize, for example, extreme code size optimization or generation of code that is kind of performant in terms of execution in favor of having, let's say, acceptable, let's say, makefile or build procedure. O2, on the other hand, it doesn't care actually about the performance of your build procedure. What does matter here is the code size generation and the performance of the generated code. Therefore, we'll see there some kind of aggressive optimization to be enabled, and we may see some kind of big impact in terms of code size as well as the performance of the execution of your program. O3 actually is similar to O2, so it includes already the O2 optimization levels, plus some extra flag actually to be enabled, or some extra options to be enabled in terms of performance and code size. Then we have, let's say, other options which favorize either only the code size optimization or performance. It doesn't try to favorize both. For instance, we have the OS. This one actually will try to take the O2 optimization and will try to disable any other sub-optimization that try to favorize the performance. OSIZE or OZ, actually this one, it will equal actually to OS or O2. However, it will disable all optimization or sub-optimization that try actually to favorize a little bit the performance behavior of your program. So here we don't care about the performance. Then we have OFAST. This one will try to favorize performance over code size. However, it is not recommended to use it because it may have an impact, for instance, for the generation of some instructions, like for the floating point unit instruction or the DSPs ones. So be careful when you are using this optimization. We have OG. OG actually is equivalent to O0, except that we have more, let's say, flexibility in terms of debuggings. So we'll have more information in the term of debug symbols, and is like user or developer friendly actually to be used. So in this case, we can deploy this optimization if we are going to debug, to have kind of extreme or extensive debug session of our program to figure out some issues or problems. Now, in our case, or for the sake of this benchmarking, we'll try to compile our code with optimization level 2. This one actually will try to do some good optimization in terms of code size and try a little bit to favor the performance of your program. So far so good. Now let's try to build again. Done. Now let's take a look. Okay, so we have the disassembly and we have the .elf. From the first view, you may think that we have, let's say, the code size is much bigger because we have the .elf bigger actually than the previous one. However, the .elf is like misleading when it's come to code size comparison. Why is that? Because we have a lot of metadata part of the .elf. It doesn't have only the pure binary. It has a lot of metadata and extra debug symbols and formations. And this is why I have generated .bin, and then I try to dump this .bin to have good idea and proper idea in terms of the real size of the binary to be loaded in the target device. What matter here for the device is the .bin, not the .elf really. So here we'll try to do the same. So I will create another directory called O2. Then I will copy over those two files. Then I will try to generate the .bin out of the .elf. So again, I will copy the location. Then opt copy. Then -o binary. Then my elf file. And finally my bin file. Done. So we have the .bin. Now it's stating 1 kilobyte, but this is not a reference because even the old program, we should have actually bigger size, has less than 1 kilobyte. So we cannot get, let's say, accurate information about the real size from Windows here. So I will dump it with the hex dump. So again, I will open PowerShell. Then I will now navigate to my directory. Okay. Done. And then I will invoke this tool hex dump. Then I'll invoke my program.bin. And finally, I will redirect the output .text. Okay, we are done. Now let's take this one out and let's put it here. Then let's open this one. This is O0. Let's rename it actually to O0. O0. I will open it. And then let's take a look into O1 or to O2, sorry. And then let's rename it O2. Already you can see that the file size here for O2, the dumped.bin, is 3 kilobytes. The other one is 4. So already you can start seeing basically the difference in terms of sizes. However, if we compare, so with the last offset of this binary for the O2 based optimization level is 1C0. For the other one, for the O0, is 270. So we already can see basically big difference in terms of code size. So you can think actually we can try to compare the assembly files. So this is for O2 and this is for O0. If we do one-to-one comparison, we can see that the program itself is different. I mean, we don't see the same here. So let's take, for example, a look into the main function. So this is our main. Okay, we have a while one here, so it is not like good reference, but even though we can compare. Yes, at least for this one, even if this is a very basic function, we can see that in the O2, we are having almost 2 instructions. That's it. We are looping here in the same location because we have only while one in our main function. For this one, actually, so the procedure call of the function was skipped. So we are trying to put the R7 to the stack. Then we do this, then this. So we have actually bigger call size. We have here 3 instructions. Here we have 2. This is, what we are having. So we can see the impact in terms of the optimization in code size as well as performance, because in terms of performance, this should be faster than this guy. Here we are trying, first of all, to push into the stack. So we are dealing basically with a memory interface to save some data. This will take some latency and some time. Then we are doing this addition. So this is extra instruction to be executed. And finally, we are looping. Here now, right away, actually, we jump it into the loop. There is no communication or interaction needed with the external memory. So guys, this was an example of the benchmarking between O0 optimization level and O2 optimization level.